Far out in the outer solar system, orbiting the giant planet Jupiter, there is a moon that looks frozen in time. Its name is Callisto, a distant world whose surface has remained almost unchanged for billions of years. Unlike many other moons that have been reshaped by volcanoes, oceans, or tectonic activity, Callisto's landscape tells a different story. Its surface is covered with countless ancient craters, scars left behind by an era when the young solar system was far more violent than it is today. Every impact, every fracture, every ring-shaped basin on Callisto is a record of that chaotic past, a cosmic archive written across its icy crust. Because of this, scientists believe Callisto may preserve one of the oldest planetary surfaces in the entire solar system, a world that has quietly watched the history of space unfold for over 4 billion years. But what makes Callisto so different from Jupiter's other moons? Why did its surface remain so heavily cratered while others were completely reshaped? And what secrets might still be hidden beneath this ancient, frozen shell? Tonight, on Stellar Depth, we explore one of the oldest landscapes in the solar system: Callisto's ancient cratered surface. Far beyond the warmth of the sun, in the vast and cold outer regions of our solar system, the giant planet Jupiter commands a family of moons that orbit endlessly through the darkness. Among them are some of the most fascinating worlds we know: volcanic Io, icy Europa, massive Ganymede, and the ancient moon known as Callisto. Callisto is the outermost of Jupiter's 4 large Galilean moons, discovered in 1610 by Galileo Galilei when he first turned a telescope toward Jupiter. At the time, these moons appeared only as tiny points of light shifting beside the giant planet. Yet, over centuries of observation and exploration, scientists began to realize that these distant worlds were far more than simple companions to Jupiter. Each moon turned out to be a complex planetary body with its own unique history, and among them, Callisto stands apart. While its neighboring moons show signs of intense activity, volcanoes erupting on Io, a hidden ocean beneath Europa, and complex tectonic features on Ganymede, Callisto appears strangely quiet. Its surface shows almost no evidence of recent geological change. Instead, it is covered with an astonishing number of craters layered upon one another, like overlapping memories frozen into ice and stone. When spacecraft first sent detailed images of Callisto back to Earth, scientists were stunned. The moon looked ancient, older than almost any other surface we had seen in the solar system. From horizon to horizon, the landscape was dominated by impact scars, large craters, small craters, enormous ring-shaped basins, and intricate patterns created by billions of years of collisions. These craters are not just scattered randomly across Callisto's surface. They cover almost every region of the moon, making it one of the most heavily cratered worlds known. To understand what this means, we have to imagine a time long before Earth's continents formed, long before life began shaping our own planet. More than 4 billion years ago, the solar system was a far more chaotic place. After the planets formed from the swirling disk of gas and dust around the young sun, countless leftover fragments still orbited through space. These fragments ranged from tiny grains of dust to massive asteroid-sized bodies. Over millions of years, they collided with the growing planets and moons, leaving behind craters wherever they struck. This period is known as the Late Heavy Bombardment, a time when impacts were extremely common throughout the solar system. Worlds that lacked strong geological activity preserved these scars as permanent records of that violent era. Callisto appears to be one of those worlds. Unlike Earth, whose surface is constantly reshaped by plate tectonics, erosion, and volcanic activity, Callisto has remained largely unchanged. Its icy crust has preserved the marks of ancient impacts for billions of years, creating a landscape that scientists sometimes describe as a fossil record of the early solar system. Seen from orbit, Callisto looks like a dark, battered sphere, floating quietly in the blackness of space. Its surface reflects very little sunlight compared to other icy moons. This darkness comes partly from the mixture of ice and rocky material covering the moon, a blend of frozen water, silicates, and darker compounds that have accumulated over time. But the most striking feature of Callisto is its overwhelming number of craters. Some of these craters are relatively small, only a few kilometers across. Others are enormous, stretching hundreds of kilometers from rim to rim. Many overlap each other, forming complex patterns that reveal the sequence of impacts over time. In places where a newer crater cuts into the edge of an older one, scientists can determine which impact happened first. By studying thousands of these overlapping structures, researchers can reconstruct the long history of bombardment that shaped Callisto's surface. Yet Callisto is not simply a chaotic jumble of impacts. Among its many craters are enormous structures known as multi-ring impact basins. These are some of the most dramatic features anywhere in the solar system. Instead of forming a single circular crater, extremely large impacts create concentric rings that spread outward from the collision site like ripples in a pond. One of the most famous of these structures is called Valhalla. Valhalla is the largest impact structure on Callisto and one of the largest in the entire solar system. At its center lies a relatively bright circular region where the original impact occurred. Surrounding this central zone are multiple rings of fractured terrain that extend outward for thousands of kilometers. If you could stand on the surface of Callisto and travel across Valhalla, you would pass through vast ridges and valleys arranged in enormous circular patterns. These rings stretch so far across the moon that they dominate much of its visible surface. Scientists believe Valhalla formed when a massive asteroid or comet struck Callisto billions of years ago. The energy released by this collision would have been almost unimaginable, far greater than any impact that has occurred on Earth in recorded history. The shock waves from that impact rippled through Callisto's icy crust, fracturing the surface and creating the vast ring patterns we see today. But Valhalla is not the only enormous impact basin on Callisto. Another structure, known as Asgard, lies nearby. Though smaller than Valhalla, it is still an immense multi-ring basin, with concentric rings stretching across hundreds of kilometers of terrain. Like Valhalla, Asgard tells the story of a catastrophic impact that occurred early in Callisto's history. These giant basins reveal something important about the moon's structure. Unlike rocky planets such as Earth or Mars, Callisto's outer layers contain large amounts of ice. When massive impacts strike an icy surface, The crust behaves differently than solid rock. Instead of forming a simple crater, the ice can fracture and flow outward, producing the distinctive ring patterns seen on Callisto. This combination of ice and rock gives Callisto its unique appearance, a surface that looks ancient, fractured, and layered with the scars of countless impacts. Yet, despite the immense violence that created these features, Callisto today is an extremely quiet world. There are no active volcanoes on its surface, no massive tectonic plates shifting and grinding against one another, no large-scale resurfacing events that erase older terrain. For billions of years, Callisto has remained largely unchanged. Orbiting far from Jupiter compared to its neighboring moons, it experiences less gravitational stress from the giant planet. This distance may have protected it from the intense tidal forces that drive geological activity on moons like Io and Europa. As a result, Callisto's interior never heated enough to trigger the kind of dramatic geological transformations seen on those worlds. Instead, its surface simply endured the endless rain of impacts that shaped the early solar system. And because nothing later erased those scars, Callisto preserves a record of cosmic history stretching back nearly to the birth of the planets themselves. Looking at Callisto is like looking back in time, not just millions of years, but billions. Every crater, every fractured ridge, every ancient basin is a fragment of that story. A story written across a frozen moon drifting silently around the largest planet in our solar system. And as we continue exploring this mysterious world, its ancient surface will reveal even more about the violent beginnings of the solar system, and about the hidden processes that shaped the planets and moons we see today. Seen from space, Callisto's surface appears almost endlessly scarred. Craters stretch across the moon in every direction, overlapping and blending together in patterns that reveal an incredibly long history of cosmic impacts. But as scientists began to study these features more closely, they realized that Callisto's cratered landscape was far more complex than it first appeared. Not all craters on Callisto are the same. Some are relatively small depressions only a few kilometers across, created by smaller meteoroids striking the moon at tremendous speed. Others are massive structures hundreds of kilometers wide, formed by collisions with large asteroids or comets during the chaotic early days of the solar system. The differences between these craters tell scientists a great deal about the materials that make up Callisto's outer layers. On rocky planets like Mercury or the Moon, craters often have sharp, well-defined rims and deep central pits. But on Callisto, many craters appear softer and more relaxed in shape. Their edges are less steep, and their interiors often seem partially smoothed out. This happens because Callisto's crust contains a large amount of water ice mixed with rock. Over extremely long periods of time, ice can slowly deform under pressure, a process known as viscous relaxation. Even though Callisto's surface temperatures are extremely cold, the ice within its crust can gradually flow, subtly reshaping older craters. As a result, many ancient impact structures on Callisto appear slightly flattened compared to similar craters on rocky worlds. This slow process of deformation gives Callisto's surface a unique appearance. Some craters have shallow floors and gentle slopes rather than steep walls. Others appear partially buried beneath layers of debris thrown out by later impacts. In fact, the sheer number of impacts over billions of years has created a kind of layered record across Callisto's crust. Every time an asteroid or comet struck the moon, it blasted material outward in a ring of ejecta, fragments of ice and rock thrown across the surrounding landscape. These fragments eventually settled back onto the surface, covering older terrain and creating subtle patterns of brighter and darker regions. Over time, this constant cycle of impact and ejecta created the heavily textured terrain that now covers Callisto almost completely. Some of the most interesting regions are known as palimpsests. Palimpsests are ancient impact basins that have almost completely lost their original crater shape. Instead of deep depressions with raised rims, these structures appear as faint circular patterns or lighter-colored regions on the surface. Scientists believe these features formed when extremely large impacts struck Callisto early in its history. The initial crater would have been enormous, but over millions or billions of years, the icy crust slowly relaxed, smoothing out the deep depression until only the circular outline remained visible. In a sense, palimpsests are the ghostly remains of ancient collisions, barely visible traces of events that occurred billions of years ago. One of the reasons Callisto preserves these ancient features so well is that its surface has experienced almost no geological resurfacing. On Earth, processes like erosion, volcanic activity, and plate tectonics constantly reshape the landscape, erasing older craters and replacing them with newer terrain. But on Callisto, none of these forces are active. There is no atmosphere to cause erosion, no liquid water flowing across the surface, no shifting tectonic plates. Instead, the moon exists in a deep freeze, its icy crust slowly accumulating the scars of impacts, while preserving older features beneath newer ones. This lack of geological activity makes Callisto extremely valuable to scientists. By studying the number and distribution of craters on its surface, researchers can estimate the age of different regions. Areas with more craters are generally older, while regions with fewer craters may have experienced some form of resurfacing. On Callisto, nearly the entire surface is densely cratered, suggesting that most of the moon's crust formed very early in solar system history. In fact, many scientists believe Callisto's surface is more than 4 billion years old. That makes it one of the oldest preserved planetary surfaces we know. Yet, even on such an ancient world, subtle variations exist. Some areas appear slightly brighter than others, particularly around younger craters. These brighter regions often contain fresh ice, exposed by recent impacts. When an asteroid strikes Callisto, it blasts away darker surface material and reveals cleaner, brighter ice beneath. Over time, radiation from space and tiny micrometeorite impacts gradually darken this ice again, returning it to the muted tones seen across most of the moon. This process gives scientists a way to estimate how recently certain craters formed. Brighter craters tend to be younger, while darker ones have been exposed to space weathering for much longer periods. Another fascinating aspect of Callisto's cratered surface is the presence of chains of craters, known as crater chains. These chains form when fragments of a single object strike the surface in rapid succession. A famous example occurred in 1994. when the comet Shoemaker-Levy 9 broke apart and crashed into Jupiter. If similar fragmented objects collided with Callisto in the past, they could have produced lines of impacts stretching across the surface. Some crater chains on Callisto extend for hundreds of kilometers, marking the path of these ancient cosmic fragments as they slammed into the icy crust one after another. The Moon's surface also contains numerous bright ray systems. These rays are streaks of material ejected during impacts, extending outward from craters like spokes on a wheel. On darker terrain, these rays can remain visible for millions of years before gradually fading. The presence of ray systems suggests that even though most of Callisto's surface is extremely old, impacts continue to occur even today. Small meteoroids still strike the Moon from time to time, adding new craters to its already crowded landscape. But compared to the violent bombardment of the early solar system, these modern impacts are relatively rare. Callisto's position in the Jovian system may help explain its quiet history. Unlike Io, Europa, and Ganymede, Callisto lies far enough from Jupiter that it does not participate strongly in the gravitational resonance that affects the inner moons. These gravitational interactions generate tidal heating inside Io and Europa, driving volcanic eruptions and possibly maintaining subsurface oceans. Callisto, however, experiences far less tidal heating. Its interior remained relatively cold throughout its history, preventing the large-scale geological activity that reshaped the surfaces of its neighboring moons. Because of this, Callisto became something like a time capsule, a frozen world that preserved the marks of ancient impacts long after other moons had erased them. This ancient surface provides scientists with a unique opportunity. By studying Callisto's craters and impact basins, researchers can learn more about the population of asteroids and comets that once filled the early solar system. Each crater represents a collision with one of those objects, providing clues about their sizes, speeds, and distribution. In this way, Callisto acts almost like a cosmic record book, storing evidence of events that occurred billions of years ago. And yet, despite its quiet appearance, Callisto still holds many mysteries. Beneath its heavily cratered surface may lie secrets that scientists are only beginning to understand, including the possibility that far below the frozen crust, hidden layers of liquid water might still exist. But those hidden mysteries lie deep beneath the Moon's ancient exterior. For now, Callisto's surface remains a vast frozen archive, where every crater tells a story of a violent collision long ago, a story preserved in ice for billions of years. While Callisto's surface tells the story of billions of years of cosmic impacts, the Moon's appearance from orbit reveals something even more fascinating: patterns within the chaos. At first glance, the countless craters scattered across the Moon might seem random, but as scientists began to map Callisto in greater detail, subtle structures began to emerge. These structures hint at processes that shaped the Moon in ways far more complex than simple bombardment. When spacecraft first flew past Callisto in the late 20th century, the images they sent back showed an astonishing landscape. The Moon was covered with craters of every size imaginable, but among them were vast, circular features so enormous that they could not easily be seen in a single photograph. These were the giant, multi-ring impact basins that dominate Callisto's ancient crust. The most famous of these structures, Valhalla, stretches across nearly half the Moon. Its central region appears brighter than the surrounding terrain, surrounded by a complex series of concentric ridges and valleys that extend outward for thousands of kilometers. These rings form an immense pattern across the icy surface, like ripples frozen into stone. To understand how such structures form, scientists had to rethink the way impacts behave on icy worlds. When a large asteroid strikes a rocky planet like Earth, the resulting crater often forms a simple circular depression surrounded by a raised rim. But when the surface contains a mixture of rock and ice, the energy of the impact spreads through the crust in a very different way. Instead of forming a single crater, the crust fractures and collapses outward, producing rings that propagate across the surface. The scale of these rings on Callisto is extraordinary. Some extend hundreds or even thousands of kilometers from the original impact site. If a similar structure existed on Earth, it would span entire continents. The formation of Valhalla must have been an event of unimaginable violence. A massive asteroid or comet slammed into Callisto billions of years ago, releasing more energy than millions of nuclear explosions combined. The impact would have melted large portions of the Moon's icy crust, sending shock waves racing through its outer layers. For a brief moment, the surface of Callisto may have behaved almost like a liquid. As the shock waves spread outward, they fractured the crust into enormous concentric rings. Over time, the molten and fractured material cooled and solidified, preserving those rings as permanent features on the Moon's surface. Today, these rings remain visible as broad ridges and valleys stretching across vast distances. Another immense basin, known as Asgard, lies not far from Valhalla. Though smaller, it is still enormous by planetary standards. Its rings form a pattern similar to Valhalla's, with ridges radiating outward from a central region where the original impact occurred. The presence of these giant basins tells scientists that Callisto experienced some of the largest impacts in the history of the solar system. During the chaotic early era known as the Late Heavy Bombardment, enormous asteroids and comets frequently collided with planets and moons throughout the solar system. Many of these impacts were powerful enough to reshape entire worlds. On Callisto, the scars of those collisions remain clearly visible. Yet even after such enormous impacts, the Moon never experienced the kind of global resurfacing that might have erased these features. This raises an intriguing question. Why did Callisto remain so geologically inactive, while other moons in the Jovian system underwent dramatic transformations? To answer this question, scientists began studying Callisto's internal structure. Unlike Ganymede, which shows evidence of internal differentiation, meaning its materials separated into layers such as a metallic core, rocky mantle, and icy crust, Callisto appears to be only partially differentiated. Its interior may consist of a relatively uniform mixture of ice and rock rather than clearly separated layers. This unusual internal structure may have prevented the Moon from developing the strong internal heating that drives geological activity on other moons. Much of the heating inside moons like Io and Europa comes from tidal forces created by Jupiter's enormous gravity. As these moons orbit the giant planet, Jupiter's gravitational pull stretches and squeezes them repeatedly, generating heat within their interiors. This tidal heating powers the volcanoes on Io and may maintain the hidden ocean beneath Europa's icy shell. Callisto, however, orbits farther away from Jupiter. At that greater distance, the tidal forces acting on the Moon are far weaker. As a result, Callisto's interior never warmed enough to trigger widespread geological activity. Instead of volcanoes or tectonic movements reshaping the surface, the Moon simply cooled and solidified early in its history. With no internal forces to erase the scars of impacts, the ancient craters remained preserved across the surface. Over billions of years, new impacts continued to accumulate, layering fresh craters over older ones and gradually building the heavily cratered terrain we see today. Yet even in this seemingly static landscape, subtle processes continued to shape the surface. One of these processes is impact gardening. Each time a small meteoroid strikes Callisto, it blasts tiny fragments of ice and rock into the surrounding area. These fragments eventually fall back onto the surface, mixing the upper layers of soil-like material known as regolith. Over millions of years, this constant churning gradually softens and blurs older features. Sharp crater rims become rounded. Ejecta blankets fade into the surrounding terrain. Layers of debris accumulate in low-lying areas. Though the process is extremely slow, it has been acting on Callisto's surface for billions of years. Another factor shaping the Moon's appearance is radiation from Jupiter's powerful magnetic field. Charged particles trapped in Jupiter's magnetosphere constantly bombard Callisto's surface. Over time, this radiation alters the chemical composition of the ice and darkens the Moon's surface material. This process, known as space weathering, contributes to the muted colors that dominate Callisto's landscape. The Moon's surface is not bright white like freshly frozen ice. Instead, it appears dark and reddish-brown in many regions, reflecting the gradual accumulation of radiation-altered material over immense periods of time. Despite its ancient appearance, Callisto still receives occasional visitors from space. Small asteroids and comets continue to collide with the Moon from time to time, creating fresh craters that stand out sharply against the older terrain. These younger craters often appear brighter than their surroundings because they expose cleaner ice beneath the darker surface layer. Over time, however, radiation and micrometeorite impacts slowly darken these fresh scars until they blend into the surrounding landscape. This slow transformation means that even though Callisto appears frozen in time, its surface is still evolving, just at a pace far slower than on most other worlds. As scientists continued studying Callisto's craters and basins, they began to realize something remarkable. The Moon's surface may provide one of the most complete records of the early solar system available anywhere. Unlike Earth, whose ancient history has been largely erased by geological activity, Callisto preserves evidence of impacts dating back nearly to the formation of the planets themselves. Every crater on the Moon represents a collision with an asteroid or comet that once roamed the young solar system. Together, these craters form a map of cosmic history, stretching back billions of years. And yet, beneath this battered exterior, scientists suspect that Callisto may hold secrets far deeper than its ancient surface suggests. Hidden beneath the thick, icy crust, there may be layers of material that have remained isolated from the surface for billions of years. Layers that could contain clues about the Moon's formation and perhaps even about the early history of Jupiter itself. But to understand what lies beneath Callisto's frozen surface, we must look beyond the craters and rings visible from space and begin exploring the hidden interior of this ancient world. Beneath the ancient cratered surface of Callisto lies a world that scientists are still struggling to fully understand. For many years, researchers believed that this distant moon was simply a frozen, inactive sphere of ice and rock, its interior as quiet and unchanging as the battered surface above. Compared to Jupiter's more dramatic moons, with Io's violent volcanoes and Europa's hidden ocean, Callisto seemed almost lifeless. But as spacecraft observations improved, new discoveries began to challenge this simple picture. In the 1990s, NASA's Galileo spacecraft entered orbit around Jupiter and began an extended mission studying the giant planet and its moons. Over several years, Galileo flew past Callisto multiple times, collecting detailed measurements of the moon's gravity, surface composition, and magnetic environment. What the spacecraft found was surprising. One of Galileo's instruments was designed to measure variations in Jupiter's powerful magnetic field. As the spacecraft passed near Callisto, scientists noticed something unusual in the magnetic readings. The moon appeared to generate a faint magnetic response when exposed to Jupiter's magnetosphere. This type of response can occur when a conductive layer exists beneath a moon's surface. On Earth, oceans conduct electricity because they contain dissolved salts. When they interact with changing magnetic fields, they can produce measurable signals. The same phenomenon could occur on other worlds if liquid water exists beneath their surfaces. The magnetic data from Galileo suggested that Callisto might contain a hidden subsurface ocean buried deep beneath its icy crust. This idea was both exciting and puzzling. Callisto was not expected to contain large amounts of internal heat. Without significant heating, the moon's interior should have frozen solid long ago. Yet, the magnetic signals hinted that somewhere beneath the crust, a layer of liquid water might still exist. Scientists began constructing models of Callisto's interior to understand how such an ocean could survive. According to these models, Callisto's outer crust may consist of a thick layer of frozen water ice mixed with rocky material. Beneath that crust, at depths of perhaps 100 kilometers or more, pressure and residual heat from the moon's formation might allow a layer of salty liquid water to remain stable. If this ocean exists, it would be sandwiched between layers of ice, sealed away from the surface by an enormous frozen shell. Unlike Europa's ocean, which may lie relatively close to the surface and experience constant tidal heating, Callisto's ocean would likely be far deeper and much colder. It might be a dark, quiet reservoir of water, isolated from sunlight and protected beneath tens or even hundreds of kilometers of ice. The existence of such an ocean raises fascinating questions. Liquid water is one of the key ingredients for life as we know it. On Earth, wherever liquid water exists, life seems able to find a way to survive. From deep ocean hydrothermal vents to underground aquifers, microbial life has adapted to environments once thought completely inhospitable. Could something similar exist beneath Callisto's frozen surface? At present, scientists do not know. Unlike Europa, whose ocean may interact with the seafloor and generate chemical energy through hydrothermal activity, Callisto's ocean may be far more isolated. Without strong tidal heating or volcanic activity, the environment beneath Callisto's crust might lack the energy sources needed to sustain complex biological systems. Yet, the possibility remains intriguing. Even a quiet, stable ocean could potentially harbor simple microbial life forms if the right chemical conditions existed. For now, however, this hidden ocean remains only a scientific hypothesis. Future missions to the Jovian system may provide the data needed to confirm whether Callisto truly contains liquid water beneath its crust. Beyond the question of a hidden ocean, Callisto's interior structure itself is unusual among large moons. Many planetary bodies undergo a process called differentiation early in their history. As they form and heat up, heavier materials sink toward the center, while lighter materials rise toward the surface. This process creates distinct internal layers, such as metallic cores, rocky mantles, and icy crusts. Earth is a clear example of a differentiated world. Beneath our planet's surface lies a mantle of hot rock surrounding a dense metallic core. But Callisto may not have experienced this process fully. Measurements of the moon's gravity field suggest that its interior may still be a relatively mixed combination of ice and rock, rather than neatly separated layers. This partial differentiation indicates that Callisto never heated enough during its formation to completely melt and separate its internal materials. In other words, Callisto may have remained relatively cold throughout most of its history. This could explain why the moon never developed strong geological activity. Without intense internal heating, there would be no widespread volcanism, no large-scale tectonic movements, and no resurfacing processes capable of erasing ancient craters. Instead, the surface simply preserved the marks of impacts, while the interior remained largely dormant. Yet, even a cold interior can still experience slow changes over time. Pressure from the overlying layers of ice and rock gradually compresses the deeper regions of the moon. Over billions of years, this pressure may have altered the structure of the ice within the crust, creating different crystalline forms that behave differently under stress. Some of these deeper ice layers may be slightly softer or more flexible than the ice at the surface. If a liquid ocean exists beneath these layers, it could slowly shift or deform under gravitational forces, subtly affecting the structure of the crust above. However, because Callisto experiences relatively weak tidal forces from Jupiter, these effects would be extremely gentle compared to those on moons like Europa. This quiet interior may be one of the reasons Callisto looks so ancient. On many planetary bodies, geological activity eventually erases the scars of impacts. Volcanoes flood craters with lava. Tectonic forces fracture and reshape the landscape. Ice flows or landslides gradually smooth out the terrain. Callisto, however, has experienced very little of this kind of activity. The moon's interior remained too cold to drive large-scale geological changes. As a result, the surface stayed largely unchanged for billions of years. The craters, basins, and fractured terrains we see today are therefore not just remnants of ancient impacts. they are also evidence of the Moon's quiet internal history. Callisto became a place where time itself seemed to slow. While other moons evolved, resurfaced, and transformed, Callisto remained largely the same, a frozen world drifting around Jupiter, preserving the earliest chapters of the solar system's story. But this quiet nature does not mean Callisto is unimportant. In fact, many scientists consider it one of the most valuable natural laboratories for studying planetary history. Because its surface has remained largely untouched, Callisto provides a unique opportunity to study impact, processes, crater formation, and the early bombardment history of the solar system. Each crater on the Moon is like a timestamp from the distant past. Together, they reveal a story that began more than 4 billion years ago, when the young solar system was filled with wandering asteroids and comets colliding with newly formed worlds. Callisto survived that era, preserving its scars in frozen silence. And as we continue exploring this ancient moon, its battered surface and mysterious interior may still hold answers to some of the most fundamental questions about how our solar system came to be. For billions of years, Callisto has drifted through space as a silent witness to the violent history of the solar system. Its surface, scarred by countless impacts, tells a story of destruction, collision, and cosmic change. But while the craters themselves reveal the Moon's ancient past, the materials covering Callisto's surface tell an equally fascinating story about how this distant world formed and evolved. Unlike many of the bright icy moons that orbit the outer planets, Callisto is surprisingly dark. When sunlight reflects off its surface, the Moon appears grayish-brown rather than brilliant white. This darker color puzzled scientists when the first spacecraft images arrived. Many icy bodies in the outer solar system are coated with relatively clean water ice, giving them a bright appearance. But Callisto's surface reflects far less light. The explanation lies in the composition of the Moon's outer layers. Callisto is not made purely of ice. Instead, its surface is a mixture of water ice, rocky minerals, and darker, carbon-rich compounds. Over billions of years, these materials have blended together through constant impacts and radiation exposure. Each asteroid or comet that struck the Moon brought additional debris. Some of this material contained complex organic molecules, carbon-based compounds formed in the early solar system. When these materials mixed with the ice and rock already present on Callisto, they gradually darkened the surface. Radiation from Jupiter's powerful magnetosphere also played a role in altering the Moon's appearance. Charged particles trapped within Jupiter's magnetic field constantly bombard Callisto's surface. Over time, this radiation chemically modifies the ice and organic materials, creating darker compounds known as tholins. These substances give many outer solar system bodies the reddish or brownish coloration. As a result, Callisto's surface slowly darkened over billions of years. But beneath this darker outer layer lies a much brighter world. When a new impact occurs, the collision can blast away the weathered surface material and expose fresher ice underneath. These younger craters often appear brighter than their surroundings, creating striking patterns across the Moon. Some of these bright craters are surrounded by radial streaks, or rays, formed by material ejected during the impact. These rays can extend for hundreds of kilometers across the surface, marking the direction in which debris was thrown outward. Over time, however, these bright features gradually fade. Radiation exposure and micrometeorite impacts slowly darken the fresh ice again, blending the crater back into the surrounding terrain. This process of gradual darkening is another reason why older craters on Callisto often appear subdued compared to younger ones. Scientists studying these features have been able to estimate how quickly surface materials change under space conditions. By comparing the brightness of different craters and measuring the effects of radiation exposure, researchers can estimate the relative ages of impact features across the Moon's surface. This technique has revealed something remarkable. Callisto's surface may have remained largely unchanged for more than 4 billion years. Few other places in the solar system preserve such an ancient landscape. Even Mercury and the Moon, two worlds famous for their heavily cratered surfaces, have experienced some geological activity that altered portions of their terrain. Volcanic eruptions, tectonic shifts, and other processes have reshaped parts of those planets. But on Callisto, almost none of these processes have occurred. Instead, the Moon remained quiet and stable for billions of years, preserving an almost untouched record of cosmic impacts. Yet the surface of Callisto is not entirely uniform. Certain regions appear smoother than others, suggesting that subtle resurfacing events may have occurred in the distant past. These smoother areas may have formed when large impacts caused localized melting of the icy crust, allowing material to flow briefly before freezing again. Such events would not erase all the craters in a region, but they could soften the terrain slightly, producing the gently rolling landscapes seen in some parts of the Moon. Another intriguing feature of Callisto's surface is the presence of fractured terrain. In certain areas near large impact basins, the crust appears cracked and broken into complex patterns. These fractures may have formed when shock waves from enormous impacts traveled through the Moon's icy crust, stretching and tearing the surface. Because Callisto's crust contains large amounts of ice, it behaves differently from the rigid rock found on planets like Earth or Mars. Under extreme pressure or sudden shock, the ice can crack, shift, and even flow slightly before solidifying again. This behavior may explain the unusual ridges and grooves surrounding some of Callisto's largest impact basins. These patterns provide clues about the thickness of the Moon's crust and the mechanical properties of the ice-rock mixture that forms its outer layers. By analyzing these features, scientists can estimate how deep the icy crust extends and how it responds to massive impacts. Callisto's crust may be over 100 kilometers thick, making it one of the thickest icy shells among Jupiter's moons. Beneath this crust may lie the mysterious subsurface ocean, hinted at by magnetic measurements. If that ocean exists, it would be separated from the surface by enormous layers of ice. But even without direct evidence of liquid water reaching the surface, Callisto's icy crust still holds important information about the Moon's history. The mixture of ice and rock covering the surface likely formed during the early stages of the solar system. At that time, Jupiter's gravity pulled vast amounts of material into orbit around the young planet, forming a disk of gas, dust, ice, and rock. Within this disk, the Galilean moons gradually assembled through countless collisions, between smaller bodies. Callisto formed in the outer region of this disk, where temperatures were colder and ice could accumulate more easily. Because it formed farther from Jupiter than the other large moons, it experienced fewer intense gravitational forces during its formation. This may have allowed Callisto to grow slowly and remain relatively cool, preventing the large-scale melting that could have triggered internal differentiation. As a result, the Moon retained much of its original mixture of materials. Over billions of years, impacts continued to deliver additional debris to the surface, gradually building the complex landscape we see today. Each collision reshaped the terrain slightly, but none were powerful enough to fundamentally transform the Moon. Instead, the surface evolved slowly through countless small changes, impacts, radiation exposure, and the gradual movement of icy materials beneath the crust. In this way, Callisto became a world defined not by dramatic geological activity, but by the slow accumulation of cosmic history. Its surface is like a vast archive preserved in ice and stone. Every crater records a moment in time when an asteroid or comet collided with the Moon. Every ring basin marks a catastrophic impact that reshaped the crust billions of years ago. Together, these features form a map of the solar system's violent youth. Looking at Callisto today is like gazing into the distant past. While Earth has erased most of the scars from its earliest history, Callisto has preserved them. The Moon remains a frozen record of an era when the young solar system was filled with wandering fragments, crashing together as planets and moons slowly took shape. And as scientists continue studying this ancient surface, Callisto may reveal even more about those chaotic early days, and about the processes that shaped not only Jupiter's moons, but the entire solar system itself. For most of its existence, Callisto has remained a silent and distant world, orbiting far from the warmth of the sun, and even farther from the dramatic geological activity seen on its neighboring moons. Yet despite its quiet nature, this ancient moon has played an important role in our exploration of the outer solar system. Much of what we know about Callisto today comes from a series of spacecraft missions that ventured into the Jovian system over the past half-century. Before these missions, Callisto appeared only as a faint dot of light in telescopes on Earth. Astronomers could measure its orbit and estimate its size, but the details of its surface remained hidden behind the vast distance separating Jupiter from our planet. That began to change in the early 1970s. In 1973 and 1974, NASA's Pioneer 10 and Pioneer 11 spacecraft became the first probes to fly past Jupiter. These missions were designed primarily to study the giant planet itself, but as the spacecraft passed through the Jovian system, they also captured the first close-up images of Jupiter's moons. The pictures of Callisto revealed a heavily cratered world, confirming what astronomers had suspected. The Moon's surface was ancient and scarred by countless impacts. However, the images returned by the Pioneer spacecraft were still relatively low in resolution. Scientists could see that the Moon was covered with craters, but the finer details of its landscape remained unclear. A few years later, 2 more spacecraft would dramatically expand our understanding of Callisto. In 1979, Voyager 1 and Voyager 2 flew past Jupiter, sending base stunning images of the planet and its moons. For the first time, scientists were able to study Callisto's surface in much greater detail. The Voyager images revealed the full extent of the moon's cratered terrain. Giant impact basins like Valhalla and Asgard became clearly visible, along with countless smaller craters scattered across the surface. These images confirmed that Callisto's surface was indeed extremely ancient. Unlike Io, whose surface appeared almost completely resurfaced by volcanic activity, Callisto showed virtually no signs of geological renewal. Its craters overlapped one another in complex patterns, indicating that the surface had remained largely unchanged for billions of years. Yet, even the Voyager missions only provided brief glimpses of this mysterious moon. It would take another spacecraft, launched more than a decade later, to truly transform our understanding of Callisto. In 1989, NASA launched the Galileo spacecraft, a mission specifically designed to study Jupiter and its moons in unprecedented detail. After a long journey through the inner solar system, Galileo arrived at Jupiter in 1995 and began a multi-year exploration of the Jovian system. During its mission, Galileo conducted several close flybys of Callisto. These encounters allowed the spacecraft to collect detailed images, gravity measurements, and magnetic field data. For the first time, scientists could study not just the moon's surface, but also clues about its internal structure. The images returned by Galileo revealed new details about Callisto's cratered terrain. Some regions showed unusual patterns of bright and dark material, suggesting that impacts had excavated layers beneath the surface. Other areas contained faint circular features, the palimpsests, that hinted at ancient basins whose original shapes had gradually faded over time. The spacecraft also observed large areas where ejecta from impacts had spread across the landscape, forming intricate textures and patterns. But perhaps the most intriguing discovery came from Galileo's magnetometer. As the spacecraft passed near Callisto, it detected subtle disturbances in Jupiter's magnetic field. These disturbances suggested that an electrically conductive layer might exist beneath the moon's crust. The most likely explanation for such a layer would be a subsurface ocean of salty water. This possibility transformed the way scientists thought about Callisto. For decades, the moon had been considered one of the least interesting worlds in the Jovian system, a cold, inactive body with little internal activity. But the discovery of a possible hidden ocean hinted that Callisto might still harbor complex processes beneath its ancient surface. If confirmed, such an ocean would place Callisto among the growing list of icy worlds that may contain liquid water beneath their crusts. Today, several moons in the outer solar system are believed to possess subsurface oceans, including Europa, Ganymede, Enceladus, and Titan. Each of these worlds has become a target of intense scientific interest because liquid water environments may offer potential habitats for life. Callisto's ocean, if it exists, would likely be very different from Europa's. Europa's ocean may be warmed by strong tidal forces from Jupiter, creating a dynamic environment where water interacts with the moon's rocky interior. These interactions could generate chemical energy capable of supporting microbial ecosystems, Callisto, however, experiences much weaker tidal heating. Its possible ocean would likely be colder, deeper, and more isolated from the surface. Without strong geological activity to mix nutrients and energy sources, the environment beneath Callisto's crust might be far less hospitable. Yet the possibility remains intriguing. Even a quiet ocean sealed beneath thick layers of ice could provide valuable clues about how icy worlds evolve over time. Beyond the question of subsurface water, Galileo's observations also helped scientists refine estimates of Callisto's size, density, and internal composition. Callisto is the third largest moon in the solar system, slightly smaller than Ganymede and Saturn's moon Titan. Its diameter is about 4,800 kilometers, nearly the size of the planet Mercury. Despite its large size, Callisto has a relatively low density compared to rocky planets. This indicates that a significant portion of the moon is made of water ice rather than solid rock. Scientists estimate that Callisto's interior may consist of roughly equal amounts of ice and rocky material. This composition reflects the conditions under which the moon formed billions of years ago. In the cold outer regions of the solar system, water ice was abundant. As the Galilean moons formed from material orbiting Jupiter, ice and rock combined to create bodies with mixed compositions. But unlike Ganymede, which eventually developed a metallic core and a magnetic field of its own, Callisto remained relatively primitive. Its interior never heated enough to fully separate into distinct layers. Instead, the moon retained much of its original mixture of ice and rock, preserving clues about the early stages of moon formation around giant planets. This primitive structure makes Callisto particularly valuable to scientists studying the history of the Jovian system. By analyzing its composition and surface features, researchers can learn how Jupiter's moons formed and evolved over billions of years. And because Callisto's surface has remained largely unchanged, it provides an extraordinary record of impact events that shaped not only the Jovian system, but also the entire solar system during its earliest epochs. Even today, decades after the Galileo mission ended, scientists continue analyzing the data it returned. Each new study reveals additional details about the moon's ancient surface and mysterious interior. Yet despite all we have learned, Callisto remains one of the least explored large moons in the solar system. Future missions may soon change that. Space agencies around the world are planning new explorations of Jupiter's icy moons, and Callisto may once again become a destination for spacecraft, seeking to understand the origins and evolution of planetary systems. For now, this distant moon continues its quiet orbit around Jupiter, carrying within it a record of cosmic history written across billions of years. And as our exploration of the outer solar system continues, Callisto may yet reveal secrets hidden beneath its ancient, cratered surface. Callisto moves through space in a slow and silent dance around Jupiter, completing one orbit roughly every 16 Earth days. From a distance, the moon appears calm and motionless, a dark sphere floating in the vast emptiness of the outer solar system. Yet, the environment surrounding Callisto is anything but quiet. Jupiter is not just the largest planet in the solar system. It also possesses one of the most powerful magnetic fields known. This enormous magnetic field creates a region of space called the magnetosphere, a vast, invisible bubble filled with high-energy charged particles trapped by Jupiter's magnetic influence. Within this environment, Callisto travels constantly through streams of energetic radiation. These particles originate primarily from the Sun and from volcanic eruptions on Jupiter's moon, Io. Io's intense volcanic activity blasts enormous quantities of sulfur and other gases into space. These materials become ionized and trapped by Jupiter's magnetic field, forming powerful radiation belts that extend throughout much of the Jovian system. Every moon orbiting Jupiter must move through this radiation environment. For the inner moons, such as Io and Europa, the radiation is extremely intense. Charged particles bombard their surfaces continuously, altering the chemistry of the ice and rock exposed to space. Callisto, however, occupies a more distant orbit. Because it lies farther from Jupiter, the radiation environment around Callisto is significantly weaker than the harsh conditions experienced by the inner moons. This difference has important consequences, not only for the moon's surface, but also for the possibility of future exploration. Even though the radiation is weaker, it still plays a role in shaping Callisto's ancient landscape. Over billions of years, charged particles striking the moon's surface have gradually altered the chemical composition of the ice. When radiation interacts with frozen water molecules, it can break them apart into hydrogen and oxygen atoms. These atoms may recombine into new compounds or escape into space. In addition to water, Callisto's surface contains carbon-based molecules delivered by ancient comet and asteroid impacts. Radiation acting on these materials can create more complex organic compounds, darkening the surface and contributing to the reddish tones observed in some regions. This process is known as radiolysis, and it slowly transforms the chemical makeup of the moon's outer layers. Although the changes occur at a microscopic scale, billions of years of radiation exposure have gradually altered Callisto's surface chemistry. The result is a crust that contains a mixture of ice, rock, and radiation-processed organic materials. Despite these alterations, Callisto remains one of the least hazardous locations in the Jovian system for spacecraft, and potentially even for future human missions. This is because its orbit places it outside the most intense radiation belts surrounding Jupiter. If humanity ever establishes a robotic or human presence around Jupiter, Callisto may serve as one of the safest bases of operation in that distant region. Some scientists have even proposed that Callisto could one day host a robotic research station or orbital outpost studying Jupiter and its other moons. Such a base could operate far enough from Jupiter's intense radiation to remain relatively safe, while still allowing spacecraft to travel inward toward moons like Europa or Ganymede. But long before such missions become possible, Callisto continues to orbit within Jupiter's immense gravitational influence. Jupiter's gravity dominates the entire Jovian system, controlling the motion of its dozens of moons. Each moon follows its own orbital path, shaped by complex gravitational interactions. The inner moons Io, Europa, and Ganymede are locked in a special gravitational relationship known as a resonance. In this resonance, their orbital periods are linked together in precise ratios. Every time Ganymede completes one orbit, Europa completes 2, and Io completes 4. These gravitational interactions continuously stretch and compress the moons, generating internal heat through tidal forces. This tidal heating drives Io's volcanoes and may maintain Europa's subsurface ocean. Callisto, however, lies outside this resonance system. Because it is not locked into the same gravitational pattern as the inner moons, Callisto experiences much weaker tidal forces from Jupiter. Without these repeated gravitational stresses, its interior remained relatively cool over billions of years. This lack of tidal heating is one of the main reasons Callisto appears so geologically inactive. While Io's surface is constantly reshaped by lava flows and Europa's icy crust may shift and fracture above a hidden ocean, Callisto's crust remains largely unchanged. The moon's ancient craters remain preserved because no strong internal forces exist to erase them. Yet, Callisto's orbit still places it firmly within Jupiter's vast gravitational domain. Jupiter's gravity not only controls the motion of the moons, but also captures many asteroids and comets that wander too close to the giant planet. Some of these objects eventually collide with the moons themselves. This process continues to add new craters to Callisto's already crowded surface. Occasionally, Jupiter's gravity also tears apart comets that venture too close to the planet. The most famous example occurred in 1994, when the comet Shoemaker-Levy 9 broke into multiple fragments before crashing into Jupiter's atmosphere. If similar fragmented objects passed near Callisto, they could create chains of craters across the moon's surface. Evidence of such crater chains can indeed be found on Callisto today. These chains appear as long lines of impact craters, marking the path of comet fragments that struck the moon one after another. Such features provide yet another reminder that even in the present era, Callisto remains exposed to the hazards of space. But compared to the violent bombardment that occurred billions of years ago, modern impacts are relatively rare. The solar system today is far calmer than it was during its earliest stages. Most of the leftover debris from planet formation has either been swept up by planets or ejected from the solar system entirely. As a result, large impacts occur far less frequently than they once did. Callisto's surface therefore changes very slowly in the present era. New craters form occasionally, but they represent only minor additions to a landscape that has remained largely frozen in time for billions of years. Despite its quiet nature, Callisto continues to capture the imagination of scientists studying the outer solar system. The moon represents a rare example of a world that has preserved the earliest chapters of planetary history. While Earth's surface has erased most traces of its ancient past through erosion and tectonic activity, Callisto still displays scars from impacts that occurred shortly after the solar system formed. By studying these craters and impact basins, scientists gain valuable insights into the population of asteroids and comets that once filled the young solar system. Each crater represents a collision with one of those ancient objects. Together, they form a geological archive spanning billions of years. Yet, Callisto's story is not limited to its past. As new missions prepare to explore Jupiter's moons in the coming decades, this ancient world may once again become a destination for spacecraft, seeking to unlock the secrets of the outer solar system. And although its surface may appear quiet and frozen, Callisto remains a world shaped by cosmic forces, orbiting endlessly within the gravitational embrace of the largest planet in our planetary neighborhood. Although Callisto appears quiet and unchanged today, the Moon has not always existed in the calm state we see now. To understand why its surface looks so ancient and heavily cratered, scientists must travel far back in time, back to the chaotic birth of the solar system itself. More than 4.5 billion years ago, our solar system was not the orderly place it is today. Instead of stable planets and predictable orbits, space was filled with countless fragments of rock, metal, and ice swirling around the young sun. These fragments were the building blocks of planets and moons, constantly colliding, merging, and breaking apart as larger bodies gradually formed. Jupiter, the largest planet in the solar system, began forming very early during this chaotic era. As its immense gravity gathered gas and dust from the surrounding disk of material, it quickly grew into a giant planet. Around this growing planet, another swirling disk of debris formed, a miniature version of the disk that once surrounded the Sun. Inside this disk, the moons of Jupiter slowly began to take shape. Pieces of ice and rock collided and stuck together, forming larger and larger bodies over time. Eventually, 4 of these bodies became the massive Galilean moons we know today: Io, Europa, Ganymede, and Callisto. But Callisto's formation may have been quite different from that of its neighbors. Many scientists believe that the inner moons of Jupiter formed relatively quickly. As material in the disk rapidly clumped together, these moons grew large enough to experience intense heating inside their interiors. This heat caused their materials to separate into layers, forming metallic cores, rocky mantles, and icy crusts. Callisto, however, may have formed much more slowly. Because it orbited farther from Jupiter, the amount of material available in its region of the disk may have been lower. Instead of growing rapidly, Callisto likely accumulated its mass gradually over a longer period of time. This slow formation process had important consequences. When planetary bodies form quickly, the energy released by countless collisions can heat their interiors dramatically. This heat melts ice and rock, allowing heavier materials to sink toward the center, while lighter materials rise toward the surface. But if a body forms slowly, much of that heat can escape into space before it has time to melt the interior. This may be exactly what happened to Callisto. Because it formed gradually, the heat generated during its formation may have dissipated before it could trigger large-scale melting inside the moon. As a result, Callisto's interior remained relatively cool and only partially differentiated. Instead of developing clearly separated layers like a core and mantle, the moon retained a mixture of ice and rock throughout much of its interior. This primitive internal structure helps explain why Callisto appears so geologically inactive today. Without intense internal heat, there was no energy source capable of driving volcanic eruptions, tectonic shifts, or widespread resurfacing. The moon simply cooled and solidified early in its history. And once its crust froze into place, the only major forces capable of altering the surface were impacts from space. During the early history of the solar system, those impacts were extremely common. Astronomers refer to this era as the Late Heavy Bombardment, a period roughly 4 billion years ago, when large numbers of asteroids and comets collided with planets and moons throughout the solar system. Some of the most enormous craters on Callisto likely formed during this violent period. Objects tens of kilometers across slammed into the moon at speeds exceeding 20 kilometers per second. The energy released by these collisions was immense, far greater than any explosion humanity has ever produced. Each impact excavated massive craters, blasted material across the surface, and fractured the moon's icy crust. Some of the largest impacts created the enormous multi-ring basins that dominate parts of Callisto today. These collisions may have briefly melted portions of the crust, producing localized pools of liquid water or slushy ice before the surface quickly refroze in the cold environment of the outer solar system. But because Callisto lacked strong internal heating, these temporary melting events never evolved into long-lasting geological activity. Instead, the moon simply returned to its frozen state after each impact. As the bombardment era gradually came to an end, the rate of impacts across the solar system decreased dramatically. Most of the remaining debris from the planet formation had either been absorbed into planets or flung into distant regions of space. By this time, Callisto's surface had already accumulated a vast number of craters. And with few geological processes capable of erasing them, those craters remained preserved for billions of years. Even today, scientists studying Callisto's crater patterns can identify which impacts occurred earlier and which happened later. Older craters tend to appear softened and partially eroded by later impacts, while younger craters remain sharper and brighter. By analyzing these relationships, researchers can reconstruct a timeline of events stretching back to the earliest chapters of solar system history. In this sense, Callisto serves as a kind of cosmic archive. Its surface preserves evidence of impacts that occurred when the planets were still forming and the solar system was filled with wandering debris. Few other places in our planetary neighborhood provide such a clear record of those ancient events. Even the moon, which is also heavily cratered, has experienced volcanic activity that resurfaced parts of its terrain. Mars and Mercury have undergone tectonic changes that altered portions of their surfaces. But Callisto appears to have remained almost completely inactive since the end of the bombardment era. This extraordinary stability makes the moon one of the oldest landscapes in the entire solar system. When scientists examine images of Callisto's surface, they are effectively looking back billions of years in time. Every crater tells the story of an ancient collision. Every ring basin marks the location of a catastrophic impact that reshaped the moon's crust long before life appeared on Earth. And every layer of debris scattered across the surface represents fragments of distant asteroids and comets that once roamed the young solar system. In a universe where change is constant and geological activity reshapes most worlds over time, Callisto stands as a rare exception. It is a world where time seems almost frozen, a silent witness to the earliest days of planetary formation. And as scientists continue studying this ancient moon, they hope its preserved surface will reveal even more about the chaotic events that shaped the solar system billions of years ago. For most of human history, Callisto remained nothing more than a faint point of light beside Jupiter. Even with powerful telescopes, the Moon appeared only as a small disk, offering few clues about the vast and ancient landscape that covered its surface. Yet, as technology advanced and spacecraft began exploring the outer solar system, Callisto slowly transformed from a distant mystery into one of the most scientifically valuable worlds orbiting Jupiter. Despite this progress, much about Callisto still remains unknown. The data collected by past missions, particularly the Galileo spacecraft, revealed many of the Moon's fundamental properties. Scientists learned about its heavily cratered terrain, its mixture of ice and rock, and the possibility that a hidden ocean might lie buried beneath its thick, icy crust. But Galileo's observations were limited. The spacecraft conducted only a handful of close flybys of Callisto, and many regions of the Moon were never imaged in high detail. As a result, researchers still have many unanswered questions. One of the most important mysteries concerns the possible subsurface ocean beneath Callisto's crust. The magnetic measurements taken by Galileo suggested the presence of a conductive layer inside the Moon, most likely salty liquid water. However, the spacecraft could not directly confirm the existence of such an ocean. Future missions will be needed to answer that question. In the coming decades, new spacecraft are scheduled to explore the Jovian system once again. One of the most ambitious of these missions is the European Space Agency's JUICE mission, short for Jupiter Icy Moons Explorer. Launched in the 2020s, this spacecraft is designed to study Jupiter's icy moons in unprecedented detail. Although JUICE will focus primarily on Ganymede and Europa, it will also perform several flybys of Callisto during its journey through the Jovian system. These flybys will provide scientists with valuable new data about the Moon's surface, interior, and surrounding environment. High-resolution cameras on the spacecraft will map regions of Callisto that have never been seen clearly before. Instruments designed to measure gravity and magnetic fields will help scientists determine whether a subsurface ocean truly exists beneath the Moon's icy crust. If confirmed, this hidden ocean could reshape our understanding of Callisto's internal structure. Scientists will also study the Moon's surface composition in greater detail. Spectrometers aboard future spacecraft can analyze reflected sunlight to identify the chemical compounds present in the ice and rock covering Callisto's terrain. This information will help researchers understand how radiation, impacts, and chemical reactions have altered the surface over billions of years. Another exciting possibility involves the exploration of Callisto as a potential destination for future space missions. Among Jupiter's large moons, Callisto occupies a unique position because it lies outside the most intense radiation belt surrounding Jupiter. The environment around Callisto is significantly safer for spacecraft and, potentially, even for human explorers. Radiation levels near Io and Europa are so extreme that unprotected electronics or human astronauts could be exposed to dangerous doses in a relatively short time. Callisto, however, experiences far lower radiation levels. This has led some scientists and engineers to propose that Callisto could serve as a future base of operations for exploring the Jovian system. In such a scenario, robotic or human outposts might be established either on Callisto's surface or in orbit around the Moon. From this location, spacecraft could be launched toward Europa, Ganymede, or other moons while avoiding the most hazardous radiation environments. Callisto's relatively stable surface and low geological activity would also make it easier to construct long-term facilities. Unlike moons with active volcanism or shifting ice crusts, Callisto's terrain has remained stable for billions of years. Large, flat regions between craters could potentially provide landing sites for spacecraft or research stations. Of course, such missions remain far in the future. The enormous distance between Earth and Jupiter, more than 5 times the distance from Earth to the Sun, makes travel to the Jovian system extremely challenging. Even the fastest spacecraft launched from Earth require several years to reach Jupiter. Yet, as technology continues to advance, missions to the outer solar system are becoming increasingly ambitious. Beyond its potential role in exploration, Callisto also offers scientists a unique opportunity to study the impact history of the solar system. Because the moon's surface has remained largely unchanged for billions of years, it preserves a record of impacts that occurred during the earliest stages of planetary formation. By analyzing the sizes, shapes, and distribution of craters across Callisto's surface, researchers can estimate how frequently large impacts occurred in the past. These studies help scientists understand the population of asteroids and comets that once filled the solar system. They also provide clues about the processes that shaped planetary surfaces throughout our cosmic neighborhood. For example, by comparing Callisto's crater patterns with those found on other moons and planets, scientists can determine whether certain impact events occurred across multiple worlds at the same time. If large impacts happen simultaneously on many bodies in the solar system, this might indicate that a major event, such as the migration of giant planets, disrupted asteroid populations and triggered widespread bombardment. Callisto's ancient surface therefore acts like a historical archive. It preserves evidence of events that occurred billions of years ago, long before Earth developed oceans, continents, or life. In many ways, studying Callisto is similar to studying the geological layers of Earth's ancient rocks, except the record preserved on this moon extends much further back in time. Yet despite all the information hidden within Callisto's surface, the moon remains one of the least explored major worlds in the solar system. Only a handful of spacecraft have ever visited it, and most of its surface has never been examined in close detail. Future missions may change that. As new spacecraft travel to Jupiter and its moons, Callisto will likely become an increasingly important target for scientific study. Researchers hope to learn more about its internal structure, the possibility of subsurface water, and the processes that preserved its ancient terrain. Each new observation may reveal additional clues about the formation of Jupiter's moons and the chaotic early history of the solar system. For now, however, Callisto continues its quiet journey around Jupiter. Its battered surface remains frozen in time, a vast landscape of craters and impact basins stretching across thousands of kilometers. A world shaped by ancient collisions, yet still holding secrets beneath its icy crust. And as future explorers, both robotic and perhaps one day human, venture deeper into the outer solar system, this ancient moon may finally reveal the full story written across its cratered surface. For billions of years, Callisto has remained one of the quietest worlds in the solar system. While other moons around Jupiter continue to evolve, volcanoes erupting on Io, icy plates shifting on Europa, and magnetic forces shaping Ganymede, Callisto has preserved a much older story. Its surface has endured nearly unchanged, carrying the scars of ancient impacts, like a frozen memory of the solar system's violent youth. When scientists examine images of Callisto today, they are not simply looking at another distant moon. They are looking at one of the oldest preserved planetary landscapes known. Every crater on Callisto represents a collision with an asteroid or comet that occurred billions of years ago. Some of these impacts happened when the solar system was still forming, when planets had only recently taken shape and countless fragments of rock and ice still wandered through space. Over time, most worlds erased this violent history. On Earth, shifting tectonic plates recycle the crust. Volcanoes flood ancient craters with lava. Wind and water erode mountains and reshape continents. Even the moon, though heavily cratered, experienced volcanic eruptions that covered large regions of its surface with dark lava plains. But Callisto remained different. Because its interior stayed relatively cold and inactive, the moon never experienced large-scale geological resurfacing. No massive volcanoes buried its ancient terrain. No shifting plates fractured the crust and replaced older regions with new ones. Instead, Callisto's surface remained largely frozen in place. As a result, the moon became a kind of time capsule, preserving evidence of the solar system's earliest era more clearly than almost any other world. Looking across Callisto's surface is like reading the opening chapter of a story written billions of years ago. The immense ring structures such as Valhalla and Asgard tell of catastrophic impacts that once shook the moon's icy crust. Smaller craters layered across the terrain record the countless collisions that occurred during the chaotic age of planetary formation. Even the faint circular outlines of ancient palimpsests reveal impacts so old that their original crater shapes have slowly faded over time. Together, these features form an extraordinary geological archive. But Callisto's importance extends beyond its ancient craters. The possibility that a hidden ocean exists deep beneath its surface has transformed the way scientists think about this distant moon. What once seemed like a completely frozen world may still contain liquid water trapped beneath thick layers of ice. If such an ocean truly exists, it would add Callisto to a growing family of icy moons that may contain subsurface seas. Europa, Ganymede, Enceladus, and Titan have already shown evidence of hidden oceans beneath their icy crusts. These discoveries have reshaped our understanding of where liquid water and potentially life might exist in the solar system. Callisto's ocean, if confirmed, would likely be much deeper and colder than Europa's. Buried beneath perhaps hundreds of kilometers of ice, it would be isolated from sunlight and separated from the surface by a thick frozen shell. Yet even in such extreme environments, scientists cannot completely rule out the possibility that simple forms of life might survive. On Earth, microbial life has been found thriving in places once thought impossible. Beneath kilometers of ice in Antarctica, deep within underground rock formations, and around hydrothermal vents on the ocean floor, where sunlight never reaches. These discoveries have expanded our understanding of where life might exist. If liquid water exists beneath Callisto's crust, it raises a profound question. Could such hidden oceans represent habitats where life might arise beyond Earth? For now, that question remains unanswered. Future missions to Jupiter's moons may help scientists learn more about the interior of Callisto and determine whether a subsurface ocean truly exists. Even if the moon's ocean turns out to be too cold or too isolated to support life, its presence would still provide valuable insights into how icy worlds evolve. Callisto may hold clues about how oceans form beneath frozen crusts and how such environments remain stable for billions of years. Beyond its scientific mysteries, Callisto may also play a role in humanity's future exploration of the outer solar system. Because it lies outside Jupiter's most intense radiation belts, the Moon offers one of the safest locations in the Jovian system for spacecraft, and possibly even human explorers. Some researchers have suggested that future missions to Jupiter might establish research stations on or around Callisto. From such a location, spacecraft could travel inward toward Europa or Ganymede, while avoiding the most dangerous radiation zones. Robotic explorers could study Jupiter's atmosphere, its magnetic field, and its many moons. Although such missions remain far in the future, Callisto's stable environment makes it an attractive candidate for long-term exploration. Yet even without human visitors, Callisto remains one of the most fascinating worlds in the solar system. It is a moon that has quietly preserved the earliest chapters of planetary history. While other worlds transformed and evolved, Callisto remained largely unchanged, a silent witness to the ancient chaos that shaped our cosmic neighborhood. From its immense impact basins to its endless fields of craters, the Moon tells a story billions of years old, a story of collisions that shaped planets, of wandering asteroids that once filled the solar system, of a frozen world that survived that violent era and still carries the marks of those events today. And as our spacecraft continue exploring the distant regions beyond Mars, Callisto will remain a destination of curiosity and discovery. Because hidden beneath its battered surface may lie answers to some of the most fundamental questions about the history of our solar system and about the worlds that exist beyond Earth. In the vast darkness beyond Jupiter, this ancient moon continues its quiet orbit, a world frozen in time, a record of cosmic history written across billions of years, and a reminder that even the most silent places in the universe may still hold secrets waiting to be discovered.